So now you all know why you're here, if you didn't already. And I want to just give you a brief introduction first to the field that I'm in, which is natural language processing. So obviously, I think a lot of you know from my talk abstract and from the title of this talk that it involves language models, among other things. But natural language processing as a whole is just about computationally processing human language. And so that includes things like spam filtering in your email, Google Translate, which I use a lot in Germany, voice assistants like Alexa, Cortana, Siri, etc., as well as this is, of course, the ChatGPT logo. But today, of course, you're here to hear about language models. So let's talk about what a language model actually is. So it's actually quite simple. It is simply a model, a box. You don't need to really know what's inside. But what it does is that it assigns probabilities to text. And this allows us to distinguish valid sequences, which generally have higher probabilities, from invalid ones, which generally are improbable. So as an example here, regardless of what's inside a language model, if you give it Heidelberg is cool, and if it's a good language model, it gives you a higher probability, like 45.2, than if you give it Heidelberg are cool, which is not grammatical, which gets a much lower probability of 3.1. And this is important because probably most of you, if you're not within the field of natural language processing, maybe you just heard about large language models within the last couple of years. But actually, language modeling as a pursuit of natural language processing has been done for decades, with a lot of stuff that changes within the box. So as an example, autocomplete, which probably we're all familiar with and which has existed like well before smartphones even, is also a language model, because really it's just trying to predict what is the most likely, what is the most probable next word, given whatever you've written so far. So if you say, are you free? Then, maybe your autocomplete says probably the next word is tonight or tomorrow or this weekend, something like that. Now, the difference between this sort of really ancient version of language modeling and large language models like DeepSeek, Claude, ChatGPT, et cetera, that we know, is essentially that they use a combination of machine learning that's at just an inconceivable scale and just massive amounts of data. So these are really the two different, these are like the differentiating factors from all of the language models that came before. And so this is what it is like in a nutshell, what I'm going to go through in more detail over the rest of this talk. And my plan essentially is to give you a whirlwind tour of how a large language model comes to be. And at each step along the way, I'm going to discuss some of the ethical issues involved. And so the three sort of main core parts of the talk are going to be talking about data that goes to train a language model, how a language model is actually trained, and then what happens when it gets deployed. And after I'm done with those parts, then I will just sort of zoom out to the bigger picture, and then we'll have some opportunity for questions. As a quick disclaimer, this is going to be a bit of a depressing talk because I will not be contrasting the ethical problems raised by LLMs with any sort of benefits of LLMs. You can go to any LLM company's website to get their take on that, and this is really what takes up a lot of space in the discourse these days. And so my goal is to kind of show you some of the things that we don't talk about that are not so prevalent in the discourse. So with that, let's start with data. And what's important essentially is that you teach a language model to model language by giving it language data, much in the same way that humans, as babies, learn language by exposure to language data. So by the age of 13, it is estimated, at least by Warstadt and Baumann, that a 13-year-old human sees about 100 million words. And this isn't unique words. This isn't 100 million unique words. This is like they have just heard 100 million words of speech from their caregivers, from people that they've interacted with at school, et cetera, by this point in their life on average. Now, the most important thing that you need to know about language models and how they differ is that the scale is just much, much, much larger. You need a lot of training data to get a language model that's halfway decent. So here's sort of the rest of the graphic, and you will notice that this only goes up to 2022. It only increases from there. But you can see sort of at a glance already that, GPT-3, which was from 2020, it's like ancient now, was already many orders of magnitude, was seeing many orders of magnitude more training data than a typical human to be able to do some form of language processing. So at this current point in time, models that see data at the trillion word scale is what's common. So this is what's estimated for ChatGPT, for example. And so I think it's important to note the contrast, because humans are very efficient learners of language. And so this is an important sort of technical challenge that we ideally would like to overcome in the field. So where does all of this data actually come from? Well, people who make language models at these companies will take data wherever they can find it. But typically, it comes from a variety of sources, including Wikipedia, scientific papers, code, books, social media, subtitles, and just all sorts of websites on the internet that don't fit into these categories. And each of these raises different sort of concerns with what the language model then learns about the world and about language, and also how it does so. So as an example, with books and subtitles, this is very often including copyrighted content. And if you, as OpenAI, are training a language model on copyrighted content and then selling a product to people and making money off of it, this can constitute a copyright violation, especially if it verbatim reproduces a book that you would otherwise pay money for. The problem with social media, of course, which I think should be obvious to everyone, is that websites like 4chan, 8chan, Twitter, etc., are really hotbeds for things like extremist content. Or, well, we can say some of them are hotbeds and some of them tolerate it. Things like extremist content, racist hate speech, Holocaust denial, sexism, transphobia, you name it. So whenever you're training a language model, you're also getting all of the horrible corners of the internet in it, essentially. And that is what, among other things, the language model is learning to model. And at a glance, you might think that Wikipedia is perhaps one of the best options for data of this list here. But it turns out Wikipedia also has some issues. So here I have a picture of the Cover Women project, which studies gender and racial biases on Wikipedia. And their work shows that women are very underrepresented in Wikipedia articles, as well as among editors of Wikipedia. And this sort of re-invisibilizes women's contributions to various fields. And the additional problem is that when Wikipedia pages get created for, say, women scientists or non-binary scientists, they are much more frequently nominated for deletion on the grounds that they are not notable enough to deserve a Wikipedia page. So the same project also finds that non-binary people are almost non-existent on Wikipedia, that the featured page tends to feature more white people than sort of would be proportionate, and so on and so forth. So there's many levels of this, and those are only a few things that they studied. So these are all the things that we know about the data that is used to train language models. But what is the actual process of it? How do language models get trained? And it turns out that the core of training a language model, a large language model today, like the ones that we know of, is actually very related to this familiar picture from before. It's literally just like autocomplete. Now we call it next word prediction, and this is the thing that large language models first get trained on. And let's just do a quick test to see if you can do it. So what the task is essentially to predict the next word. So if I tell you the capital of France is, and tell you to predict the next word, does anyone want to yell out the answer? Yeah. F. That's a really good answer. I didn't expect that, but it's a really good one. Do you want to go?
Paris.
Yeah, that's the one that I was expecting. But still, very good answer. So yeah, Paris. So as I mentioned before, what language models are is basically a probability distribution of human language. And so a good language model should assign a higher probability to Paris compared to other alternatives. So in other words, we should see a probability distribution that looks something like this, where Paris gets a very high probability, Berlin and Lyon, which are not the capital of France, get a much lower probability, and also other unrelated words, which I don't have space to show you, like quickly or elephant, should also get very low probability. Similarly, if you changed the question so that you were asking the capital of Germany is, then you would want Berlin to be assigned the highest probability, and you'd want the other ones to be assigned lower probability. So this is kind of the end state that you want. This is the end state of a fully trained language model. But how do we actually do it? How do we train a language model to model probabilities in this way, even for extremely long contexts of many sentences stitched together or many paragraphs stitched together? Well, to answer this, I obviously need way more than 30 minutes to do it accurately. So I'll show you like a simple abstracted version where all I tell you is that a language model is a neural network. So this is sort of a very common visualization of a neural network. And all that it is connections from inputs to outputs. So inputs would be a sequence of words, and outputs would be also words, but then you'd be modeling probabilities over these words. And in between, you just have a lot of different paths that can be taken, essentially, and that can change the values that you end up with at the end. So the circles are called neurons because it's a neural network, and the edges that go between them, the connections, those can be sort of strengthened or weakened in order to change the connections that and combinations that a language model or that a neural network makes in order to connect the input in different ways to get different outputs. So the process of training a language model, or really any neural network, just involves updating these connections, the weights of these connections, and strengthening some and weakening others, and doing so automatically with mathematics rather than magic, and also rather than, so you don't go in as an expert and change things yourself. You don't know really what is going on in there. So this has advantages and disadvantages because it means that we as, humans, we don't need to know everything there is about human language to be able to build a system that models it. We can sort of let it automatically figure things out based on the data. But it also has disadvantages in the sense that, as I said, you don't really know what's happening with each neuron or each connection. And if one connection is strengthened, you may not be able to say what that means or why that means something, or it wouldn't necessarily also make sense in a human understandable way. So that's essentially the core of machine learning. And when you start out, before you have a fully trained language model, all of the connections between the neurons are just random. So there's no real relationship between any of the inputs and any of the outputs. And you remember I told you the inputs the sequence of words, the outputs probabilities. So maybe when you give the input the capital of Germany is, then you just get some random set of probabilities at the end. And in this example case that I have, it even assigns Lyon a higher probability, a slightly higher probability than everything else, which is, of course, the wrong answer. But if you remember, we have our training data, and our training data tells us what the correct answer is. In our training data on, let's say, Wikipedia or books or whatever else it might be, we have sentences where the capital of Germany is continued with the word Berlin. And so we know that Berlin should be the correct answer. And so what we can do then is use a combination of linear algebra and calculus to trace a route backwards through the connections automatically and figure out which connections should be strengthened or which connections should be weakened in order to make Berlin go higher and the other ones go down. So we just crunch the numbers essentially and update the connections. So what does it look like after one update? Some connections essentially are strengthened, and the probability of Berlin got like a little bit higher, and the probability of Paris got lower. So we have improved, but you might see that the probability of Berlin is still not the highest, it's still Lyon, so we have to do it again. So we do it again. Now even more connections are strengthened, and Berlin is now winning like it's supposed to be. But we can still sort of go further. Now this, of course, is just a single text example that I'm showing you for illustrative purposes because this is a talk. But as I said before, this is happening on the scale of trillions of words. Absolutely enormous scale that I obviously cannot really display on a single slide. And the idea is essentially that with all of these neurons and with all of these connections, a language model can develop some high-level abstractions about all of this data. And then you get a next word predictor that is actually quite useful and quite effective as an approximation of human language. So you keep going for more rounds until the probability distribution doesn't change that much. So at this point, maybe you end and you have the final probability distribution that I showed you originally, where Berlin is clearly the highest and the others have been suppressed to quite low values. So even though this is very high level, I hope it demystifies some of the technical side of things for you a little bit. And I think what my most important takeaway for you is essentially that it's not magic, right? Like it's literally just math. And we also control everything about it. We control what are the inputs and outputs. We control how many neurons to include, how to stack them in these layers that I have here, how much you strengthen the connections by, when you stop training, and so on. And when you tweak all of these settings that you can control, you can get different results. You can get better or worse language models. And that's essentially how the process works. Now, unfortunately, next word prediction is not actually such a great and useful language model in the same way that ChatGPT is. So it's not useful in practical scenarios. So let's just look at an example of what that looks like. So if I type to just a language model that has been pre-trained on next word prediction, if I type, what is the capital of France? What is the capital of Germany? The language model is trained to just say what is the most likely thing to come after text that looks like this. And so what you get is, what is the capital of Spain? What is the capital of Switzerland? What is the capital, so on and so forth. So in this sense, it's not answering a question, because that's not the most likely continuation of this text that you begin with. But the most likely continuation is just more questions about the capitals of countries. And so what you need to do after this sort of training process is you need to do something called post-training. And post-training is essentially what allows you to then have this kind of chat interface where maybe you say, what is the capital of France? What is the capital of Germany? And a model responds with the capital of France is Paris, the capital of Germany is Berlin. Now, the nice thing is this part of things requires way less data. The post-training requires way less data than the actual training process. But the sort of counterpart to this is most of the stuff that's happening at this stage requires human intervention. So humans need to judge whether this is a useful answer or not, whether it's a helpful answer or not, whether it's concise or not. And humans are also involved in judging, for example, whether a model is generating something that is very racist or sexist and kind of suppressing that. So what happens is you originally learn this model where you're just learning how to predict the next word, and then you add some stuff on top to make sure that it's, answering questions, because that's what we find useful. I won't really go into the technical part of this process, but as I mentioned, post-training relies on human feedback. And so now this is sort of the end of the technical part, and we will go sort of back to some of the ethical concerns. So with regards to the humans that are involved in this process, the very unfortunate thing that you may have already heard about is that they are treated very badly. So this is a Time Magazine exclusive on OpenAI paying Kenyan workers less than $2 per hour to make ChatGPT less toxic. And not only are they paid very little for their work, but also they're labeling very, very disturbing content that has caused psychological distress among a lot of the workers. Like one of them that was interviewed was saying that it destroyed him completely. And unfortunately, this is also not a one-off, but a recurring pattern with gig work and with crowdsourcing across all sorts of LLM companies, and also across many countries, not just Kenya, but also Venezuela, a lot of countries in the global south mainly. And partly it's also, I think the companies see this as necessary to keep costs down because they spend so much on the training process, which is very intensive in terms of needing computer chips that are special and data centers that are very, very expensive. But to be honest, even the part that comes before this post-training, the actual training, is not completely ethical and great. So as I mentioned before, the scale of data that you need to train a large language model today is huge, but also the large language models themselves are also huge. The primary thing that has been responsible for success in large language modeling has been increasing the number of parameters. So the number of circles, the neurons that I showed you in that diagram before. So GPT-1, which is at this point like a very old model, had 117 million parameters. And GPT-3 had 1.5 billion. And now ChatGPT, we don't actually know exactly how many parameters it has, but it's been estimated from 2 trillion parameters to 8 trillion parameters. And I drew the smaller version because I still wanted you to be able to see the other circles when I drew this on the slide. And I also wanted to point out that the first 3 models, the really old on the scale of my field ones, are the only ones that can run on my computer here. And so all of the ones that are larger than that, you need a GPU cluster. You need much more expensive computers even to be able to run them. And I should also emphasize that the MacBook scale sort of number that I've given you is just for running a fully trained language model. If you want to train it, then you definitely can't use a MacBook anymore. So to train such huge large language models, you need gigantic data centers. And in fact, so data centers that are specialized, like this one in Texas, for LLM training and LLM deployment are actually so large that they're now called hyperscale data centers. There are more than 1,000 worldwide at the moment, and of course they're increasing. And I think it's important to sort of show you what it looks like and to tell you about it, because I think when we go on a website and we use ChatGPT, it's very easy to forget that there's all this real technical infrastructure behind it that's supporting it. Because it's very far away from us, it's hidden from us, not just the data centers, but also the workers who are doing the dirty work, essentially, to build us these models. And in fact, these data centers, although probably there's not one that's going to come up in Heidelberg, wherever they do appear, they're really unpopular because whenever they enter a community, they use absolutely enormous amounts of energy and water because they're just hooked into the local grids for both. And they generate a huge amount of noise pollution and air pollution. So from very, very far away, you can hear them, which I found interesting. I've actually never been to or near a data center, but I've sort of read about this. And it's a thing I didn't know. So hyperscale data centers are used not just to train these sorts of language models, but also to serve them, to deploy them and to serve them to users around the world who look at them online, including us in Germany. So now let's turn to some of the consequences of the wide deployment and availability of LLMs. So this is not an LLM. Obviously, this is the Therac 25. I don't know if any of you are familiar with this, but it's essentially it's an old computer-controlled radiation therapy machine. So it delivers radiation, basically, to people who have cancer. And it had a software bug that sometimes gave people a radiation dose that was like more than 200 times too high, which resulted in their death. So this is a really important case study that we learn in software engineering and in software engineering ethics more specifically, because engineers dismissed what people were saying who were using the system. And of course, this resulted in more harm because they didn't just stop and investigate. They were like, nah, this is not happening. Does anybody want to guess how many deaths this caused before it was taken off the market or stopped being used? Yeah.
1,000?
6. Yeah, 6 deaths, and that was it.
Okay.
Just 6. Not even 6,000, 6 deaths. This is the Wikipedia page on deaths that are linked to chatbots, and I can tell you that the number is already more than that. And this includes sort of, yeah, I know there's children in the room, but this includes sort of multiple different types of death as well. It also includes children. And there are also less extreme health consequences like AI psychosis, which perhaps some of you have heard of, because these language models have a tendency to just agree with whatever you say. And this is, again, related to what it's optimized to do. It's optimized to be helpful, to be an assistant. And so this can often sort of reinforce things like delusions when they're in very early stages, and they might be controlled if people were, I don't know, normally interacting with other people as opposed to interacting more and more with chatbots. On a less serious note, of course, there's lots of amusing what are called hallucinations by these language models. So one example that went viral was when a user asked how many rocks I should eat to Google, and the Google summary said that UC Berkeley geologists said that you should eat at least one small rock per day. Now, this is obviously not true, and don't eat rocks per day. I feel like I have to say this because there are children in the room. But the sort of point here is essentially that large language models are not optimized for facts or truth, right? They're optimized, as I showed you, to predict the most likely sequence of language that follows a text or that answers a question. And so this has to have, this, by design doesn't necessarily have to have any connection to reality. And that's why you get problems like this. And of course, the impact on our skills and behavior, which is still, it's very new, it's being studied at the moment. But in general, we are tending to offload more of our skills, so we're losing some of our skills, and we are maybe even losing the ability to learn new things because learning requires friction, and if we don't persist through that friction, then, how are you really going to learn new things? So this is kind of some of the consequences that are appearing of large-scale deployment of large language models. But as I mentioned, I wanted to talk about some bigger picture questions that this raises. So for me, I think the overarching question can be summed up as, what sort of world do we live in versus what sort of world do we want to live in, and how do we get there? At the moment, large language models approximate distributions of language. So this doesn't give us any guarantees. As I said, this is why we get things like hallucinations. This is by design. So is this really the best tool to be doing factual things? Probably not, because you can't get any guarantees that you will get factual outputs. Another thing that I have sort of mentioned in my abstract and mentioned also at the beginning is that there's a concentration of power and resources in the hands of a few players. There's a few large language model companies. They control a lot of stuff. They have a lot of data, I think even from Germans, because Germans use a lot of these companies. And this is not ideal. And of course, the use of large language models has been, raising a lot of questions about the nature of education, science, work, etc. So is education really just getting a piece of paper so that you can get a job? Or is it about learning how to think, learning how to read, ask critical questions, and so on? Because if it's about the former, then of course you can do all of your homework assignments by just getting a large language model to finish them, so you just get the paper at the end of the day and use the rest of your time for more useful things to you. But if it's about something more, then what is the role of the university in this? Similarly with science, is it about the fundamentally human pursuit of understanding of the world, or is it simply about results that cause technological process, and it doesn't really matter who it comes from, whether it's a machine generating them or humans pursuing it? And also labor. What kind of labor will we do? Do we want to be, the ones thinking the high questions and outsourcing all the sort of work like cleaning my dishes? Or do we want, models to be the ones making art, and we are the ones slogging and doing sort of, boring work? So I want to raise these questions, and I kind of don't want to tell you what to think, because in the end, I think you have to answer these questions for yourself, and not just for you personally, but for all of us collectively. And I believe that some of these things, like why are we doing this, and do we want to even do this? Do we want to spend so many resources, so much of the environment towards making large language models in exchange for what we get out of them? I believe this is a question that we should get to answer democratically as a society, which we're not able to do at the moment because of that concentration of power and resources in the hands of a few players. Just like we are democratically going to decide for or against a wind farm in Heidelberg by considering all of the arguments for and against all sides and then voting on it. So I think we can all agree that Companies are pushing very hard for an agenda that's very pro large language models, which of course they stand to make a lot of money off of. And these companies say that large language models can make art for us and can code for us and be our therapists and our friends and collaborators and so on. But I really think that what I believe is that we lose something as a society and as humanity when we stop making art or, getting good at a craft or talking to each other. And if we instead sort of substitute a model's generations for all of these things. So I do want to end on a positive note. So my call to action is to embrace your humanity. Really embrace the friction of learning something new, the joy of connecting with people, of authenticity and skill in all of its forms. You can do it by trying a new weird hobby, like using photosensitive paper or, crochet, which is, I guess, not that weird. Or you can connect with people over football or card games or whatever. Make some art by hand for someone that you love. I think all of these things are more important now than ever to remember what makes us human and to value that. So thank you.